In the wild world of string theory, it's often the simplest questions that lead to the biggest revolutions. Today, we're diving into one of those, the open string. It's this tiny, vibrating strand of energy, but unlike a closed loop, it has two ends. And that brings up a really simple but profound question. What in the world do those ends do?
So here's our roadmap. We're going to start with the basic puzzle of a string having ends. Then, we'll look at the only two possible rules that can govern those endpoints. That's going to lead us, believe it or not, to the birth of these incredible objects called D-Branes. From there, we'll listen to the song a quantum string sings, and finally, we'll zoom out to see what this all means for the bigger picture.
All right, let's jump right in. Part 1, a string with ends. I mean, the name says it all, right? The defining feature of an open string is that it's, well, open. It has two endpoints, and that one tiny detail, as we're about to see, changes absolutely everything.
So this is the big question, right? This is the mystery we're unpacking. We actually have a pretty good handle on the physics that describes the middle part of the string. But to get the full picture, we absolutely have to know what's happening at the boundaries. What are the rules of the game for these two little endpoints?
What you're looking at here is what physicists call a world sheet. It's basically a map of the string's entire journey through spacetime. And the equations that describe the physics for the middle of this sheet, for the main part of the string, are well known. But right at the edges of the sheet, the equations just stop working. They don't tell us anything. We need a special set of rules, just for the ends.
And that's where something called boundary conditions comes in. Think of them as the official rulebook for the string's tips. Without these rules, our whole description is incomplete. It's like a story with no ending. And as it turns out, when you do the math, there are really only two ways this can go.
Which brings us nicely to part 2, rules for the endpoints. Let's meet the two possible fates that can befall the end of a string. Okay, so you've got two options here. On one hand, you have what's called the Neumann condition. This is easy to picture. The endpoint is completely free. It can zip around wherever it wants, whipping back and forth at the speed of light, kind of like the tip of a cracking whip. Then you have the total opposite, the Dirichlet condition. In this case, the endpoint is completely stuck. It is locked to one single position in space, just like a guitar string that's bolted down to the bridge of the guitar. And this diagram really shows it perfectly. You've got the Neumann end, free as a bird, and the Dirichlet end just stuck. A single string could even have one of each. Now, for a long time, physicists were totally cool with the Neumann condition. A free end. Sure, makes sense. But the Dirichlet one, that one was a real head-scratcher.
Yeah, a little odd is putting it mildly. It just seemed wrong. Why on earth would a fundamental object, a building block of the universe, be arbitrarily nailed down to one spot in space? It felt like a mathematical trick, not real physics. So for years, most people just kind of ignored it. It was this weird, awkward possibility that didn't seem to have any physical meaning.
But that very oddness, that thing everyone ignored, turned out to be the clue to a massive revolution in physics. Welcome to part 3, the birth of D-Branes. This is where we finally solve that nagging puzzle.
This is the question that blew the whole thing wide open. Just think about it. If the string's end isn't just mathematically fixed for no reason, if there's a physical reason it's stuck, then it has to be attached to something. But what? What kind of object could even exist in spacetime that a string could end on?
And the answer required this huge shift in perspective. The fixed point, that weird Dirichlet condition, wasn't just some rule you write in an equation. No, it was a signpost. It was pointing to a brand new kind of object, a real physical thing that actually exists in our universe. The string isn't just stuck, it's anchored to something.
And they gave that something a name, the D-Brane. That D is for Dirichlet, of course, honoring the weird boundary condition that led to its discovery. So a D-Brane is a physical place, a surface or a whole subspace, where open strings are allowed to end. That odd mathematical rule was actually our first glimpse of a totally new, fundamental building block of reality.
And get this, D-Branes aren't just static parking spots for strings. They're dynamic objects themselves. They can move, they can vibrate, they can interact, and they come in all sorts of different dimensions. A D0 brane is like a point. A D1 brane is a line, or a kind of string itself. And a D2 brane is a two-dimensional surface, a membrane.
Okay, so we've got our strings, and now they can end on these D-Branes. This brings us to the really fun part, part 4, a quantum string song.
What happens when we stop thinking about this as a classical string and start treating it like a quantum object? What kind of music, what kind of particles does it create?
In the quantum world, different vibrations correspond to different particles. More intense vibrations mean more energy, and thanks to our old friend E equals mc squared, more energy means more mass. This formula you're seeing here is basically the string's songbook. It tells us the exact mass of the particles that are created by all the different ways the open string can vibrate while it's attached to a D-brane.
And when you actually work through the math, a couple of incredible things pop out. The ground state, the string's lowest possible energy, which is no vibration at all, actually predicts a particle called a tachyon. Now, its mass squared is negative, which signals that this simple model is a bit unstable, but look at the next level up. The first excited states, the lowest possible vibrations. The math shows, incredibly, that they are all massless.
And this family of massless particles is just amazing. It actually contains two totally distinct types. First, if the string vibrates parallel to the brane it's attached to, it creates a particle that looks and acts exactly like a photon, the particle of light. It's a gauge field, but here's the catch. It's trapped on the D-brane. Second, if the string vibrates perpendicular to the brane, it creates particles that represent the motion of the D-brane itself, as it wiggles around in the other dimensions. The string's song is literally describing the physics of the brane it's attached to.
So this all leads us to our final section. Let's zoom out and look at the bigger picture. How does this whole idea of open strings and the D-branes they end on fit into everything else we know about the universe?
This diagram right here shows the final crucial piece of the puzzle. Open strings don't live in a vacuum. They can interact. And as you can see, two open strings can come together and their endpoints can meet and join up. And when that happens, they form a single closed loop. They become a closed string.
What this means is that open and closed strings are fundamentally inseparable. They're two sides of the same coin. Any theory that has open strings and D-branes must also have closed strings. It's not optional. And since we think the graviton, the particle that carries the force of gravity, is a type of closed string, this means D-branes are deeply intrinsically connected to the theory of gravity.
Which leaves us with one final mind-bending thought. We just discovered that particles like photons, the particles of light, are trapped on the D-brane. What if other particles are too? What if the stuff that makes up you and me and this entire planet? What if all of it is just the vibrations of open strings forced to live and move on a giant D-brane? Could it be that our whole, vast, three-dimensional universe is nothing more than a membrane floating in a much larger, higher-dimensional space? It's a wild idea, and it all started with that one simple question. What do the ends of a string do?